In the early 80s, if you owned a home computer, magazines were your lifeline. The articles taught you things about the computer that the manuals didn't. The ads were your only resource to find out what was available. And oh, the program listings. Also known as type-ins, this was free software for gaming, managing your checkbook, teaching you about geography, and pretty much anything else you can imagine. All you had to do was type it in. But don't make any mistakes. Rainbow magazine was the premier magazine for the TRS-80 Color Computer. And starting in January of 1983, they gave us all a gift. Accompanying each program listing, a series of cryptic codes that helped you spot any typing errors as you went. But there were several issues, and 1 year later they overhauled the system. Today, we explore exactly how this all worked, what went wrong, and how they fixed it. In the process, we'll explore the internals of the Color Basic Interpreter itself. It's hard to describe to those who don't know just how exciting it was to get a new issue of a CoCo magazine. My favorite part were always the type-ins. They meant that my CoCo would soon be doing something it had never done before. And my uncle had the biggest of all the CoCo magazines, Rainbow magazine. When I visited him, I would sit at his CoCo and spend hours typing in programs from Rainbow. The most exciting programs to type in would be machine language games. They could do things basic programs couldn't, and were sometimes as good as games you would normally have to pay money for. I particularly remember playing Marathon a lot after typing it in. By the way, check out what the author wrote before the Marathon listing. Dude left his phone number. It was a different time. The machine language listings would mostly be a series of data statements with tons of numbers. It's hard enough to type in basic code with English words perfectly, but look at these thousands of numbers. It's nearly impossible to get them all perfect. In January of 1983, Dennis Lewandowski took a stand. He gave us all a late Christmas present in the form of Rainbow Check. It was a small basic program that poked a machine language routine into memory that would help catch typos. From that issue onward, they promised every listing would come with a series of codes. When you finish typing a line from the program that has a corresponding code, you stop, hit the down arrow, and compare the code printed at the top of the screen with the code written in the magazine. If they're different, you know you made a mistake since the last checkpoint. So let's take a step back and review what just happened. In a fairly small amount of code, this routine managed to insert itself into the basic interpreter in order to trap that down arrow key press. But remember, the basic interpreter is written in ROM. You can't just go and change the ROM. And then it somehow examined the lines of code that we typed in BASIC, and it calculated a check code that you could then compare with the published codes in the magazine to see if you did it right. How did it do any of that? This code here is how it embeds itself inside the basic interpreter. We'll talk in detail about how it works later on. All of this is just to be able to print the check code once it's calculated above, which really only leaves these few lines that actually calculate the check code itself. So let's focus on how that works. The basic interpreter maintains 2 pointers or addresses in memory. The pointer at 1.9 always points to the very beginning of your program, and the pointer at 1b always points to the end of your program. So all that code is doing is subtracting the end pointer minus the start pointer to calculate a size. And that's all these check codes are. They're the current size that your program should be at a given point while typing it in, expressed in hexadecimal. Because hexadecimal looks complicated and they want to feel important. Some of you might already see a flaw with this approach, but let's watch it in action to see what happens. So I'm starting here from scratch. I've got no program installed. If I hit the down arrow now, we see that the code is 2. That's not a problem. That's not crazy. It's just counting a couple null bytes, but that's fine. It's consistent about it. So let's add the first line to our code. And we'll hit the down arrow again, and now we're up to hex 10. So far, so good. Let's add our next line. Just going to create a string variable. Hit the down arrow again, and now it's bigger, which makes sense because the program is bigger. But what if I'd made a mistake in line 10? Let's go ahead and change that O to a 0. So now this is our program. If I hit the down arrow again, it's still 21, and just to prove it, it's still 21, even though I have a mistake. And the reason is the number 0 takes up 1 byte just like the capital O does. So common mistakes like that are not going to be caught. But let's keep on going. I'll have another variable here. I'll set it equal to the result of sign. If I hit the down arrow, it goes up some, which is great. But what if instead of sign, I had typed peak? So now my program looks like this, and if I hit the down arrow, it's still 2F, and to prove it, 2F, even though my sign is now a peak. And you might be thinking, but sign is 3 letters and peak is 4 letters. What you're seeing here is the result of crunching, which we will talk about later, but the point is I can make some pretty serious mistakes. I can type a wrong command, I can type a wrong function, I can type a wrong character, and it won't catch it in some cases. To be fair, all these flaws were known about at the time, and the author warns us about them. But he claims, and I agree, this flawed rainbow check is way better than the nothing we had before. Fast forward 1 year to February 1984, and H. Allen Curtis publishes the new Rainbow Check Plus. This is not a simple patch to address the problems with the original Rainbow Check. It's a complete redesign of how everything works. It also can work in just 4K, which the original Rainbow Check couldn't, and there's a version for the Micro Color Computer, or MC10. They didn't provide an assembly language listing, so I went ahead and disassembled it, cleaned it up with some comments, and we're going to run through exactly how it works. These first 2 lines are all about deciding where in memory to squeeze the Check Plus code. This is a crude memory map that the basic interpreter sets up, and if you look toward the bottom, we have this thing called string space. Normally the basic interpreter will leave no room for this, and have string space butt up right against the very end of RAM. This code grabs the pointer to the string space, and calculates just enough room for itself. This clear command then ensures we'll have just enough room for the Check Plus machine language code here, just enough for the small amount of string space we'll need, leaving as much room as possible for BASIC and the BASIC program. One of the nice things about this approach is that by checking this, and basing where to poke the machine language code into on the result of that means that whether this machine has 4K or 16K or 32K, it will always make use of as much memory as we have, by keeping itself butted up against the very end of RAM. This is a nice upgrade over the original code from Rainbow Check. Instead, it just looked at where the end of the RAM lived, and made 2 cases. Either we were 32K or 16K, and it would decide where to put the machine language code based on that. Rather than taking cases, the new code just does a calculation to decide how much room to leave, and then starts poking at that point. And that's exactly what the next 3 lines do. They read through all the machine language bytes and poke them into memory right at this tiny little wedge it left for itself. And the next line of code is awesome. It catches any errors you might have made while typing in all of this code by just adding together the values of all of the numbers and comparing it with a known sum that it should add up to. It's kind of like a Rainbow Check Plus for the Rainbow Check Plus code, because you don't have Rainbow Check Plus running to check what you're doing until you've typed in the Rainbow Anyway, it's very cool. So let's dive into this. The basic program will immediately execute this code to install the Check Plus into the keyboard routine. No real difference from the original Rainbow Check, but let's finally see how this actually works. Color Basic sets up a bunch of what they call RAM vectors. For certain subroutines that add-ons to BASIC, such as Extended Color Basic or Disk Extended Color Basic, these provide hooks that the add-on BASICs can take advantage of. It's a way for the older BASIC to call into the newer BASIC by using a level of indirection. Rainbow check takes advantage of the RAM vector in particular for the console in subroutine. The idea is that anytime someone wants to call the console in subroutine, they don't call it directly, they call RVec4, and then RVec4 is a simple jump into the console in routine. The console in routine is in ROM and you can't mess with it, but RVec4 is in RAM, thus the RAM part of the RAM vector. So all Rainbow check has to do is insert itself in the middle. It finds the RVec4 pointer and points it to the Rainbow check routine. And then when the Rainbow check routine is done, it calls into where RVec4 used to call, the console in routine. Once this code has executed to insert the check routine into RVec4, the basic program has completed its job. The basic program terminates and you're free to erase it from memory. But this check routine remains. It remains very close to the end of RAM. And anytime you hit a key, it will run. The very first thing it does is to compare the key you press with the down arrow. If it's not the down arrow, it immediately goes into the console in and does nothing. Otherwise, the real fun starts to happen. To better understand what it's doing, let's take a look at how the basic interpreter crunches its command before it executes it. Right now we're spying on memory starting at 2DC, which is the basic interpreter's line buffer. So I'm going to start typing a command and you'll see that as I type it, the bytes get filled out. These bytes are simply ASCII codes for all the characters I'm typing, and on the right you can actually see the text for those ASCII codes. It starts filling out the buffer at the second byte for some reason. Watch what happens when I hit enter. The print is gone. It's replaced with 87. 87 is a token that represents the print command. But otherwise everything is as it was before. We have the space, the double quote, and the howdy do. This is called crunching. The interpreter looks at all the keywords it recognizes, and before it executes it or saves the line as part of a program, it converts all of those keywords to their tokens. This makes the programs take up less space, and it makes it faster to execute them. When we enter an entire basic program line by line, each line is represented like this. First the line number, and then the code for that line, but in crunched form, and finally a single 0 byte to indicate we're done with the line. In this manner, as we enter each new line, it gets stored as its own series of bytes. Following the very last line of the program is just a 0 word. And just before each line number is a pointer that points to the next line. This isn't strictly necessary, but it is an optimization that makes a lot of things much faster. It allows the interpreter not to have to scan through every byte of every line when it wants to skip around. And now that we see this, we can describe what the check routine does in a simple sentence. It just adds together all the green bytes. The line numbers and the crunched code, the values of those bytes are just added together. The pointers on the left of the screen are ignored. The sum is maintained in an 8-bit register A. So once the sum goes over 255, it cycles back to 0. So it is possible to make a mistake and to be in an unusual situation where somehow your checksum is still correct. But this would be quite rare, because the typical kind of typo you might make, like screwing up a line number or a character or a command or a function, is going to result in a different sum. You'd have to make a lot of weird errors that all somehow cancel each other out to get a sum that accidentally matches what's published in the magazine. The way it prints also underwent an upgrade from the original Rainbow check. This was the original printing code and it just did everything manually. It broke the word down into bytes and the bytes into nibbles and then figured out how to print each nibble as a hexadecimal character. But the check plus code to do the printing is just this, plus a few bytes of data at the end. Recall the line buffer we talked about before. This is that area in memory where as you're typing a basic command, your characters are stored here temporarily while they get crunched. Well, the first thing this new printing code does is it goes into the line buffer, and 2 bytes in, it stores that sum that it calculated. And then it commandeers the basic interpreter to execute this command. Print peak of 734. 734 just so happens to be the address of that byte that it just wrote the sum at. And that's it. This is the line that calls that subroutine to execute a basic command. And before it does that, it takes these bytes at the end, which are the tokenized crunched version of the print peak 734 command, and stores the address of those bytes here at a special location that the ROM knows to look at to get its command to execute. It primes the A register with the first byte of the command, and the ROM takes it from there. I find this a really clever way to do it. It makes the code much smaller and just takes advantage of the fact that the ROM already knows how to print stuff. So let's try it out. I have no program in the memory right now. I'll hit the down arrow, and I get a 0. That makes sense because there are no bytes to add up. You'll notice, by the way, rather than hard coding the number to appear up here in the upper left, which could make it hard to read if there was other stuff here that it was kind of merging with, since it lets BASIC do the printing, it just shows up on the next line. Now we're at 98. And what happens if I change that last O to a 0? 67, a very different number. Now we're at 148. And if I were to change sign to peak, 149. And if you're wondering why they're off by exactly 1, that's because the token for peak is exactly 1 more than the token for sign. Another bonus here is now everything is printed in decimal because that's how BASIC does it. No more intimidating hexadecimal to wrestle with. There's an interesting lesson to be learned in this. If you were just a casual observer and you saw the change from those 2-byte rainbow check codes to the new 1-byte check plus codes, you might be thinking, oh boy, they lost a byte of precision. Now there will be more collisions and we'll make mistakes without catching them because we'll end up with the same check codes. But actually it's the reverse. Yes, we lose 1 byte of precision, but it's more important to pay attention to what is the data that we're actually presenting in the first place. Presenting a 2-byte size code is way less useful than a 1-byte checksum. If you'd like to take a look at the code, there is a link in the description. You can find the fully commented version of the Rainbow Check Plus code that you can review on your own. As always, thank you for watching, and hey, let's be careful out there.